Alright, moving on to chapter 12 in our textbook, covering eligibility traces. So this is a different way, different than the n-step return that we saw previously, a different way to combine Monte Carlo approaches. Look at the return from a full trajectory, and temporal difference, or specifically TD0 methods that that propagate value using an online Bellman update from the immediate neighbors, right? So this is a different way, a more sophisticated way compared to n-step bootstrapping. And we're going to cover that, the eligibility traces, along with, we'll also see how to combine this with function approximation. Okay, this approach. So up to now, we covered TD0, where we propagate state or action values for immediate neighbors, one-step TD learning. Right? We saw that in Q-learning or Q-learning variant and a SARSA variant. And we know that this results in biased samples, because it's biased because we have to use an estimation of the next state. We also saw Monte Carlo approaches known as TD1. I'll show you in a second why these are known as TD1, where we update state or action values according to the return from a full episode. Right? And we saw that this results in high variance in the samples, and it must be on policy. And we also already saw a combination of these two in order, in an attempt to balance bias and variance, which was the n-step return. We've discussed those previously. What's the intuition behind n-step return? So our goal is to estimate the value of some state in our state space. Let's just, for the sake of this example, let's just say that it's S0. The state at time step 0, right, the first state that we see, while balancing both the bias and variance. So estimating the state value for S0 based on one-step TD learning is done as follows. So this is the online Bellman update rule as we've seen it before. It's simply, we say that our estimation of the state value is the immediate reward that we see at time step 1 plus gamma, the discount factors, time our current state value estimation of the next state. In this example, it will be S1. And as we discussed previously, this has high bias because of the bias introduced in our approximation of state S1. But it has very low variance. That is, if we'll visit S0 again and take the same action, we'll probably, in many cases, see the same immediate reward and the same next state. I mean, there is some variance there, but it's significantly lower than sampling the full trajectory. What would happen if we do two-step TD learning? In two-step TD learning, we set our estimate for S0 as the immediate reward in the first time step, plus the discounted immediate reward in the second time step, times twice discounted the state evaluation in state S2, the state that we'll see in 2 steps into the future, right? If we do two-step TD learning, this will have lower bias, right? We observe 2 true reward instead of 1 true reward as in one-step TD learning. So it has lower bias but higher variance. The probability of seeing S1 and then S2, of reaching S2, is lower than the probability of just reaching S1, right? So it has high variance because we rely on seeing very specific 2 immediate rewards and 2 specific states. And that wasn't the case in one-step TD learning, where we only assume to see 1 immediate reward and 1 next state. And of course, we can push this forward to n-step TD learning, where we simply sum all of the discounted immediate rewards that we see in n steps, and then we add an n discounted estimation of the state that we see after time step 10, time step n. This has even lower bias, we observe the true rewards for n steps, but it has even higher variance because the probability of following this exact trajectory diminishes, usually exponentially, we'll see an example soon, with n, with the number of steps. So let's look at a very specific example that will give us a good intuition regarding this variance, this probability of sampling very specific trajectory. So assume that every state action pair leads to one of two outcomes. So let's assume that we have a very simple MDP, right, with two states, SA and SB. And each action we choose will lead with 0.5 probability either to the same state or to the next state. Okay? In such a simple MDP, what would be the probability? What is the probability of sampling a specific two-step trajectory, right? So we started at some state, seeing a specific next state and a specific next state. What is that probability?
Is this 0.5 into 0.5?
Right. So 0.5 to the power of 2, because we start at some as 0, assuming that we always start from that as 0. Okay, let's assume that it's deterministic. The probability of seeing a specific S1 is 0.5, and then the probability of seeing a specific S2 is again 0.5. Right, so it's 0.5 to the power of 2. What is the probability of sampling a specific n-step trajectory?
0.5 to the power n.
Right. It goes... diminishes exponentially with n, right? So the trajectory probability diminishes exponentially with n. And this is for a sample MDP, but as long as you have these probabilities, transition probabilities, that's commonly the case, that the probability of sampling a specific trajectory diminishes exponentially with the number of steps in that trajectory. Okay, and so usually our goal in n-step return would be to find an n that optimizes some combination of bias and variance, right? And so we can see a nice example here, right on the left, or here, where our estimation of g of the sum of return, starting from a specific state, is very biased if we start with, if we do one-step return, right? So the variance is very low, our noise is very low, but it is biased. You see, it's above the true value. The true value, let's say, it's the blue line. As we consider more and more n's, you can see how the confidence interval grows, but it grows and it starts to surround the true value, so it has less bias with more variance. And indeed, commonly we see that as n grows, we see less bias in our G estimation, but higher variance. Okay, so this leads us to our new method that tries to balance between the variance and bias of these estimations, of n-step estimation. And this is denoted lambda return. So consider the n-step return for every possible value of n. Okay, or we will consider the n-step return for every possible value of n. So we'll consider the return for n equals 1, for n equals 2, n equals 3, and so on, right? Where for each one, we use the exact same definition as before of the n-step estimation at the current time step t until time step t plus n, which is just a summation of rewards, of observed rewards, discounted rewards for n steps, and then the estimation of the state after n steps. Now we're going to assign an exponentially decaying weight, it decays with n, for each such return. And that will represent the decaying likelihood of the sampled trajectory. How confident are we in this n-step return, in this specific n? Now specifically, we have a very specific way to set these weights, and we set the weight for any n as follows, as 1 minus lambda times lambda to the power of n minus 1. Why? I'll show you in a second. But for now, just accept that this is the weight that is assigned for each n-step return. By the way, lambda is a hyperparameter. It's a hyperparameter that considers how fast is your confidence decaying in later or in longer horizon as trajectories, in more steps. And so now we set the adjusted return as a weighted sum, right, based on the weight that we just defined, a weighted sum of all of these n-step returns, n1, n2, n3, and each one multiplied by the specific weight that we just defined. Now, the specific weights were defined in such a way that guarantees that they all sum to 1. Okay, and that makes sense for a valid weighted sums. So it gives a weighted average over all, for such that all of the sum of the weighted values will actually represent a weighted average. Right? It's an average value over all n-step returns. It's more than that, it also guarantees that you can set a lambda that is close to 0 and you'll get, well, TD0, and if you set a lambda that is 1, you'll get TD1, Monte Carlo. I'll show it to you in a second. But another thing that is important to know is that this definition of weights is relevant to the infinite horizon case, right? So it will sum to 1 at infinity, at n equals infinity. However, we know that in many cases we have MDPs that have a bounded trajectory, right? If you have a bounded trajectory, you know that all episodes end after 1,000 steps. Then the weight has a slightly different definition, which takes into account this capital T, which is the bound on the episode length. Okay, and so in those cases, we define the weight slightly differently. As we can see here, we add this term. We add this term to all of the weights in order to guarantee that still all of the weights sum to 1, and TD0 is TD0 and TD1 is TD1. Okay? And I also include here the specific proof regarding the bounded horizon adjustment. It's fairly simple and you're welcome to go over it. Okay, and so now we can look at the weight solution that we saw so far, and we can validate that indeed the one-step return is given the largest weight, right? It has the weight of 1 minus lambda. The two-step return is given the next largest weight, which is 1 minus lambda times lambda. Just recall that lambda is between 0 and 1. The three-step return is given the next weight, right? It's 1 minus lambda times lambda squared, and so on. So that makes sense. It actually, the weights reduce exponentially. This is exactly the behavior that we looked for. And now, more than that, we can play with the values of lambda between 0 and 1 and get some interesting extreme cases, right? Or anything in between. What would happen if we set lambda to 0? What will happen to all of the weights?
They'll all be... The first one will be 1.
Right.
The rest will be 0.
Right.
That will just be TD learning.
Right. This will be 1. Yes. The rest will be 0. It will be one-step TD learning.
Yes.
Right. Also known as TD0. Yeah, this is what. What will happen if we set lambda to be 1?
The first one, all of them will be 0.
All of them will be 0.
All of them will be 0. Except for the new term that we added.
Except for the last one in the episodic case, right? So this is for the episodic case, this is the last weight, and it will equal
1.
1, yeah, it will equal 1. That is, we have which algorithm?
Monte Carlo.
The Monte Carlo algorithm, right. So TD1 is indeed the Monte Carlo algorithm, at least for the bounded horizon case, bounded horizon version. But we know that Monte Carlo requires an episodic setting, right? And indeed, this is the case here. So you can see that now you can understand, you go back and understand why one-step TD learning, I always called it TD0, or commonly called TD0 also in the textbook, and why Monte Carlo is commonly written as TD1 in the textbook. So this is the reason that we use this notation. Okay, so the lambda return gives us an alternative way of moving smoothly between Monte Carlo and one-step TD learning methods that can be compared with the n-step TD learning, because in both cases we have an estimate of capital G, right, for any given time step. But they have a different way of doing that, where in the lambda return case, we actually take into account the probability of seeing a specific trajectory, specific n-step trajectory. Okay, and of course we can extend these methods to approximation methods, as we've done before, right? So instead of it's simply changing our current estimation, the estimation that we're trying to fit. We can either use n-step return, one-step return, Monte Carlo return, or lambda return, right? All of them are estimates, hopefully low bias, low variance estimate as much as possible of the true value that we're trying to estimate, of the V of ST. Okay, so this would mean that for each visited state, we need to look into the future in order to estimate the lambda return, right? Because I need to say, I need to look at all of the n steps, I need to look at all of the n steps returns that are, at all of the n step returns to determine the, and to do a weighted sum of them in order to determine the lambda return. Okay, moving forward. So this actually is not a good idea. Usually we don't want to do to look into the future, because that requires us to do a post-mortem updates. That is, to go all the way to end the episode and only then update everything backwards. We want to avoid that, because normally we would like to perform online updates, specifically if we're in a non-episodic case. There's no episode to complete. So we would like to update on the fly each of our states as much as possible. So we want to update the weights on every step of an episode rather than only at the end of the episode, or maybe in a non-episodic setting. It will allow us to equally distribute the computation time rather than all at the end of the episode. And of course it will allow us to be applicable to continuous control problems rather than just episodic problems. So the way we do that is, instead of doing post-mortem updates, we do backward updates. But now, okay, so the main idea here is, at every state you can look n steps into the past and do a very specific update to that previous state, right? So the state that you just visited before the current state, you can go back there and do a one-step update to the state that was one step behind us. And you could go 2 steps into the past and do a 2-step updates for that state, and so on. So we have a way in which for each state that we visit, we go back in time and update everything backwards. Right? And that allows us to do an online computation. Why can we do that? I mean, you might say, you know, I can't do that because I need all of the n-step returns in order to average them. And I'll tell you no, because I know the exact weight that is assigned with each one of them, so I can do them one at a time. Right? I can say, oh, one step one step in the past. I want to update you based on one step return, but with a very specific weight. And I'm going to add the two-step returns and three-step return later on, and I know with what way to do that. But for now, I know how to update one-step return with the relevant weight. Again, this allows us to truly do online updates.